The next speaker is Francesco Muia. His title is Lorentzian Vacuum Transitions.
Yeah. So thanks a lot for the invitation. It's nice to meet you all, even if only virtually. And I hope you're fine despite the circumstances. So today I will tell you about the content of a couple of papers that developed in collaboration with Fernando, Veronica Pasquarella, who is a student in Cambridge, Sebastian Cespedes, who is a postdoc in Madrid, and Shanta De Alvis, who is in Boulder, Colorado. And the story behind this talk starts with the cosmological constant problem. Out of the many possible proposed solutions to these problems, the one that probably works better is the anthropic selection. At the very least, because we have string theory that in principle can provide a landscape of vacua that could cover finally all possible cosmological constant values. I agree that this is not very appealing, but as Fernando likes to say, this is the worst solution to the CC problem, except for all the others. But the crucial point here is that in order for this solution to work, you need to really populate all the possible vacua in the landscape. And this is the main idea behind this talk. Vacuum transition was studied initially by in these two seminal papers by Coleman and De Lucia, both with and without gravity. But after 40 years, there are still some subtleties that are not fully understood, as I will tell you. So the main idea, the guidance question that we want to answer is how to populate the string landscape. And we already know that eternal inflation, the slow roll eternal inflation is not enough, because in string theory, you would like to populate vacua that are not described by the same potentials, because you can change fluxes. And when you change fluxes, you are changing effective field theory, basically. And there are a few mechanisms that help us in this task that refer to these seminal papers that I will mention, that I will explain later. They are Coleman De Lucia, Brown Teitelbaum, Farigut and Guven, FGG, and Fischler, Morgan, and Polczycki. I will tell you about the differences. But there are some more specific questions. For instance, there's been some claims in the past that when you have a potential like the one in the figure, that is very similar to what we have in explicit constructions of string theories, like KKLT and the large volume scenario. So you have a decompactification direction. There is no CDL bounds that interpolate between the two vacua, so the field always escape towards the compactification limit. Then it's interesting to ask whether from a given de Sitter it's possible to up-tunnel to all de Sitters to cover the full landscape, and if it is possible to do so starting from a four-dimensional Minkowski vacuum. More in general, the long-term goal of this enterprise will be to have a mechanism that provides a spontaneous compactification from 10-dimensional Minkowski vacuum to de Sitter in 4 dimensions. And more in general, it's also interesting to challenge the validity of Coleman De Lucia. So let me start with a brief review of quantum transition, starting from the simplest example, which is WKB in quantum mechanics. We have the Schrödinger equation that can be solved using the ansatz e to the I action. And using the semi-classical expansion, one can solve the equation order by order. For the purposes of this talk, I will be only interested in the leading order of the action S0. So one can solve the Hamilton-Jacobi equation on energy eigenstates. You can decompose the action in this way, and you get this expression from which you can compute the action just by integrating the momentum. So 2 observations. The first one is that you always get 2 solutions in this way, because the momentum appears quadratically in this equation. And under the barrier region, S0 is imaginary. So given this, one can define the transition rate as e to the minus exponential of the imaginary part of the classical action. There are many subtleties to this picture, of course, that are very nicely reviewed in this recent paper by Andreas and the collaborators. The fact that you're under the barrier, so you get an imaginary momentum, is crucial for the fact that we can use Euclidean techniques, because it's equivalent to having an imaginary time. And one can show very easily that the WKB result is equivalent to the Euclidean action evaluated on the bounce. What is the bounce is simply the solution that in the reverted potential goes from x1 to x2 and goes back to x1, like in this picture. And then it's easy to show that the two results are equivalent. One observation is that if the action evaluated on x1, so on the false vacuum, is not 0, then one needs to subtract its value. And this is what we will refer to as background subtraction. In quantum field theory, the picture is very similar with some few modifications. First of all, we have now an infinite dimensional space of field configurations. And the potential energy of a static configuration now is given by the sum of the gradient energy and the potential energy integrated over space. So since you have an integral here, it's not possible to tunnel homogeneously everywhere, because it will be like tunneling through an infinite barrier. But it's possible to tunnel locally through the nuclear creation of bubbles. And there are many ways of interpolating between two field configurations. The bounce is the one that, or the ones that minimizes the integral of this functional view. Also, it's interesting to know that quantum tunneling conserves energy. So in quantum field theory, up tunneling is forbidden. It's possible to show also that there is a theorem that the bounce with the lowest action is has SO4 symmetry. So once this symmetry is assumed, we are in the Euclidean space. The equation of motion for the field is very simple. It's the equation for a classical particle with friction in the inverted potential. And using these boundary conditions, the solution always exists in this form. Once the bubble materializes, if the pressure wins over the tension, they go in opposite directions, then the bubble expands, and it's possible to get the evolution of the bubble after nucleation doing an analytical continuation. Since we know that the solution will be a function of rho, the radius in a Euclidean space, we can just rotate a Euclidean time in time and get the hyperbola that we expect for this bubble expansion. Now, Coleman-DeLucia is basically the same idea, but with additional gravity. So first of all, why one would include gravity in the game? There are a few cases. So first, for instance, if the scales are close to the Planck mass, the scales of the problem, or also if the radius of the bubble is comparable with the horizon of the space-time, and if there is a space-time and or topology change. Now, of course, you want to patch two space-times together, but you have GR that gives you some constraints on this. So you cannot patch them randomly. You have to satisfy the junction conditions. And the junction conditions are basically amount to solving the Einstein equations in the vicinity of the wall. If you have a thin brain with some tension, for instance, what you need to impose is that the metric is continuous and there is a jump in the extrinsic curvature, which is given by the tension itself. In this setup, in this context, one can study the sitter to the sitter transitions. And what you have to do is basically what you also do in flat space-time. You need to find solutions that interpolate between the two vacua. But this time you don't have only the scalar field, you also have the metric. The task is simpler in thin wall approximation when you approximate the wall with the brain. because in that case, the action can be written like a sum of 3 terms, and the 3 simple terms, then that depend only on one coordinate, which is the position of the wall, and then one can minimize the action and find the solution. And in this case, the result is given by this expression. But the point, the crucial point here is that while in a flat space we knew that the configuration, the SO4 symmetric configuration, is the most relevant one, here this is done by analogy with the flat space limit. There is no theorem here to ensure this. And here we see 2 possible solutions. These are portions of S4 spheres in Euclidean space, because you can choose 2 different combination of the signs of the extrinsic curvature inside and outside the wall. And these solutions, you see, preserve the SO4 symmetry related to the S3 that goes in this direction. Okay, one thing to notice is that if you want to study Minkowski to de Sitter transition in this context, so you take the H of the outside to 0, you get a 0 probability. So up tunneling in this context is forbidden from Minkowski. Then one can ask how do we get the evolution of the bubble after nucleation? So since here we have assumed the SO4 symmetry, we have a metric that looks like this. And the way to get the Lorentzian version of this metric is to analytically continue one of the angular variables, so that one gets this metric. You see this metric, this part is equivalent to the metric of a de Sitter in 1 dimension less. And in these coordinates, one can describe the diamond, the orange diamond. You see in this Penrose diagram, the psi of the Euclidean space becomes this coordinate psi, and these black lines are slices of constant psi. So since in Euclidean space, all the fields depend only on psi, also in Lorentzian space, all the fields will depend on psi and will be constant on these lines. And on this slice, the slice of nucleation of the bubble, which is the red line, the field has to interpolate between the true vacuum and the false vacuum. The observer is at the center of the bubble on this side. And assuming that the field is placed at a constant field, it follows one of these psi equal to constant trajectories. And then for continuity, once you go in this region, you have the field to be constant on these slices, the green slices that correspond to open slices. So due to this argument, it's typically thought that an observer at the center of the bubble, the nucleated bubble, will see an open universe. And this is presented as a compelling outcome of the quantum tunneling. So a consequence of Coleman-Deluccia, basically. Having this picture in mind, in which you have a scalar field that tunnels in a fixed scalar potential. Okay, so this is the picture for a Coleman-Deluccia. But as I said, there are a few issues, as suggested, for instance, in this paper, in this recent paper by Blanco, Pillado, Deng, and Vilenkin. Basically, because the CDL formula, including gravity, is proposed just by analogy with the flat space limit. So, for instance, we don't know if really the SO4 symmetric instanton is the most relevant one. And this is, since this has important consequences, it's good to revisit and challenge this assumption. Also, there are other questions that one can ask. First of all, for instance, we have seen that Minkowski to de Sitter uptunneling is not possible in this using the Coleman-Deluccia picture. And it's interesting to revisit also this claim. And more in general, general solutions such as Schwarzschild to de Sitter are hard to get. Farigut and Guven tried, for instance, to compute the tunneling rate for Svarshi to the sitter transition, and they had problems, as I will tell you later, because they found an instant that was singular. And on top of this, there is huge literature on the negative mode problem that arises in Euclidean computations of quantum transitions. So it's good to have an orthogonal approach to try and address, or at least approach, these problems. And so we try to study basically quantum transitions using the Hamiltonian formalism for tunneling that amounts basically to solving the Wheeler-DeWitt equation. Here H is the Hamiltonian of the system, psi is the wave function associated with a given space-time, and G is the metric of the field space. And we took inspiration from this paper by Fischler, Morgan, and Polchinski that I will tell you about later. The picture is very similar to what happens in quantum mechanics. You have a semi-classical X function. So you can find the action basically integrating the momenta. You see that here you have not only an integral over fields, but also an integral over space. And what we want to compute is basically the ratio of the squares of the wave functions associated with the nucleated the space-time over the background space-time. So what we need to compute is this difference here. So let's see this applied to a simple example, which is the Vilenkin and Hartog-Login wave functions. In this case, we are in mean superspace. So the only field that is present is the scale factor. This determines entirely the metric. And Hamiltonian in this case is very simple. And you see this f of a that plays the role of a potential as a barrier form in the a direction. So since you start from a equal to 0 and you tunnel to the classical turning point, which is in 1 over h, remembering that the Hamiltonian is 0 by the Hamiltonian constraint, these are typically referred to as tunneling from nothing scenarios. Yeah, you can solve the Wheeler-DeWitt equation, and you find the action basically integrating the momentum. And doing so, integrating up to the classical turning point, you find this expression, which is the Vilenkin and Hartog-Login wave function, which is associated with the full bubble of the sitter. Of course, here we have two integration constants, C1 and C2, that can be fixed by fixing the boundary conditions. In particular, Hartog-Login requires that an outgoing wave at infinity. The tunneling exponent corresponds to mass. Relations between a few different kinds of transitions that I will talk about. The first one is a transition alla CDL, which is when you have a fixed scalar potential and the field with the two minima, say, and the field tunnels in this potential. Another possibilities are transitions alla BT, in which the space-times are fixed by the cosmological constants. And this, we argue, describe better the situation of string theory, in which you have two different effective field theories that cannot be described within the same scalar potential. Also, I will talk about transitions with a wall, in which you have you preserve only the SO3 symmetry, and the entire SO4 symmetry of the mini superspace is broken by the wall. And transitions in mini superspace, in which you go from one entire de Sitter bubble to another entire de Sitter bubble. I will start by the transitions alla BT with a wall. So in this context, it's interesting to ask whether the trajectory of the wall in the Coleman-De Lucia scenario depends on the assumption about the SO4 symmetry. So in order to answer this question, we solved the junction condition equation that takes this form, with this potential. You see this effective potential. So again, we have a tunneling from nothing, because here the energy is fixed to -1, R equal to 0 is here, and you tunnel up to the classical turning point, which is at R0. And interestingly, we found basically exactly the same trajectory as in CDL. And we recovered the SO31 symmetry of these slices, these open slices, without any reference to the Euclidean SO4 symmetry. And also another interesting point is that the asymptotic speed is smaller than the speed of light. So now once we have the bubble trajectories, one needs to compute the tunneling exponent. So you start with an SO3 symmetric metric, and you want to find the action by integrating over the momenta. Here the action has two contributions, the bulk and the wall. Here all the hats refers to the quantities evaluated at the wall. And you have again two solutions as in the Euclidean case, except that here you have portions of S3 instead of portions of S4, because we are in dimensionless. And the two solutions depend on the signs of the extrinsic curvature on both sides of the wall. And here you are preserving the SO3 symmetry instead of SO4, which is broken by the wall. We can compute the action, which takes this form, and the final result is given by this expression, which is very similar to the CDL formula that I showed before, but not exactly the same, because still here there is one step missing, which is the subtraction in the background. In particular, this expression that I show here is symmetric under the exchange inside with the outside, while the background subtraction breaks this symmetry. And the background corresponds to a full de Sitter sphere, so basically an orthologing or Vilenkin wave function. Once you subtract the background, so basically you compute this ratio, we find for eta equal to +1 exactly the same result as in Coleman-de-Luccia. So this is the first result. So basically, we are able to recover the Coleman-de-Luccia tunneling exponent using the Hamiltonian formalism. And interestingly, sending H outside to 0, so taking the limit of Minkowski to de Sitter, you see that the numerator is finite, but the denominator is blows up. So this is exactly the same problem that we had in Coleman-de-Luccia, for which the probability for Minkowski to de Sitter was going to 0. Here we see that this depends entirely to the from the background. Now, once we have studied this de Sitter to de Sitter transitions, it's also interesting to study more general transitions, in particular Schwarzschild to de Sitter. We have seen that in the de Sitter to de Sitter case, we have this kind of picture, and this corresponds to a tunneling from nothing. But in general, Schwarzschild to de Sitter transition, the initial state is not necessarily nothing, because the potential takes this form. So you see, you have two kinds of solutions. The first one are bubbles that start at 0, hit the barrier, and go back to 0. And another kind of solution is the one that starts at infinity, hits the barrier, and goes back to infinity. Now, of course, the most interesting solution here will be the one that is able to tunnel from solutions of type A into solutions of type B. And this is the main idea behind the papers by Farigut and Guven that I mentioned at the beginning. So they computed the tunneling, the transition rate for this kind of transition using Euclidean techniques, and found that the instanton is singular. But then this computation was redone by Fischler, Morgan, and Ponchisky using Hamiltonian techniques. And they found that there is no problem in the calculation, so validating the FGG result. But now this is interesting for us because we can take the m equal to 0 limit in this case. That will correspond again to Minkowski to de Sitter, because we are sending the mass of the black hole to 0. Now, the mass of the bubble is given by this expression. This is computed by imposing the junction conditions. And once the interesting fact is that once you take the limit m going to 0, the potential you see loses the first classical region, and we are again in a situation in which you have tunneling from nothing, because you from r equal to 0 in the under the barrier region, you tunnel to the first classical turning point. And one thing to note is that Minkowski does not decay. So when I say Minkowski to the sitter, doesn't mean that Minkowski decays. It stays there outside the bubble. So this conceptually can be seen as similar to the de Sitter as a resonance proposal of Maltz and Susskind. You can compute the action in this case, which is given again by this ratio. And you see that in this case, taking this limit, the transition rate is finite, contrary to the case of Coleman Deluccia, in which you send the cosmological constants to 0. Now, a few observations. We have seen that the choice of the sign is crucial for these computations. So there's no clear, so it's a matter of choosing the boundary conditions, right? There's no better choice unless you impose some boundary conditions. But we can say that the plus sign always dominates unless one chooses some particular boundary conditions that make this term dominating. And also another consistency check that we have done that seems to work better for eta plus 1 is the detail balance consistency check. So detail balance, basically, the statement is that the ratio of the probabilities should be proportional to the exponentials of the entropies that give basically the number of microstates associated with a given space-time. And S for the Sitter is pi over h squared. And this works for eta equal to plus 1. So with this interpretation, it's also clear why the Minkowski to the Sitter case works in the case of mass of the black hole going to 0, because the entropy there is going to 0, the entropy of the black hole. While in the de Sitter case, we are sending the radius of the de Sitter to infinity. So the area of the horizon goes to infinity, and the entropy goes to infinity. And the probability goes to 0. Okay, so an open question is about the open or closed universe. It seems to us that in the BT transitions, there's no preference for the open universe, because you have two different cosmological constants here and here. And the observer at the center of the bubble can choose any slicing he likes without any problem. But still, we are investigating, because they will be all homogeneous. But we are still investigating what happens when you add matter to the picture. Then, as I said, there are also mini superspace transitions. In this case, you start with an SO4 symmetry. There is no wall. The matrix is determined completely by the scale factor. And the simplest possibility is that you have a tunneling from the Sitter to nothing, and then again back to the Sitter, in given a potential like the one that I presented for the Hartog-Login wave function. In this case, the tunneling exponent will be the difference of the Hartog-Login wave functions, so with the proper choice of the signs. And this contributions is typically larger than CDL. Here you will have, you see, an entire de Sitter going into another entire de Sitter. But then there are also classical transitions. So, for instance, there is a flyover, which has been proposed recently by Blanco Pillado and collaborators, in which you have a potential like this. And so imagine you give a kick to the field that could come from some thermal fluctuations, for instance. If the kinetic energy is large enough here to overcome the barrier, you get a transition, and the field settles into the other minimum. And there are also similar other similar solutions such as Hawking Moss. But on top of this, there are also other classical paths that can give a transition in mini-superspace, which is which need contracting the universe. So when you have a contracting universe, you know that, and you want a bounce, so you want at the end a universe that is expanding. You know that at the bounce h dot has to be larger than 0. This means that if k is -1 or 0, then you need to violate the null energy condition in order to get a bounce, and so you need the phantom matter. But if you have k larger than 0, so 1 as a closed universe, then this is not needed, and you can have classical trajectories with a smaller with a kinetic energy which is smaller than the height of the barrier, contrary to the flyover case. This is an example of this. You see the universe is initially contracting, and then it starts expanding again. And here the field starts in the false vacuum. The potential is always this one. So false vacuum minus 0.21 and true vacuum in 0.01. You see the field starts in the false vacuum, and then it oscillates, and then it settles into the new vacuum. Okay, so the main points is that we have tried to recover the de Sitter to de Sitter transitions from a purely Lorentzian computation in order to validate the Coleman-de Luccia formula. The final result agrees with the CDL, but there are subtleties that need to be understood. In this formalism, it seems that Minkowski to de Sitter transitions are allowed in the limit in which you take a black hole mass to 0. But again, are not allowed in the usual CDL limit of the cosmological constant to 0. And we find that for BT transitions, the open universe is not compelling, but now we are investigating what happens if matter is altered. And also we observed this non-standard classical transitions with the contracting universe that we were not aware of and need further investigation. And there is a lot of work left to do. We want for sure to extend the FMP to include scalar fields, to keep studying this non-standard classical transitions and explore other phenomena using this formalism, such as the bubbles and nothing, and also phenomenological consequences of vacuum transitions. So I think I have 2 minutes and a half.
Yes.
Left. Okay, so in these 2 minutes, I would like to point out another topic that comes from this point, the phenomenological consequences of vacuum transitions. So we know that one possibility is the production of gravitational waves from, for instance, in vacuum transitions, for instance, from bubble collisions. Now, here I'm showing you a plot that includes many sources of gravitational waves at high frequency in the range between the kilohertz and the gigahertz. We find this very interesting because they all come from some beyond the standard model physics. So it would be very nice to have a way to detect them. But of course, these are beyond the range of all the current gravitational wave detectors. So exactly to explore this possibility, we organized 1 year ago one workshop about the challenges and the opportunities of gravitational waves at high frequencies. And where we gathered basically people who have been working in this direction, both from the theoretical and the experimental point of view. And we recently published the outcome of this workshop in this white paper. Now, it's interesting that even with very little effort in this direction, because there is no clear astrophysical source in this frequency range, there are like order 20 detectors that have been proposed in the last 30 years or so. And it's interesting to look at the historical perspective. So if you think about the history of the LIGO, in the 60s, there were a few different technologies proposed for gravitational wave detectors, among which, for instance, bars and interferometers. But to start with, interferometers weren't very interesting. You see, in the Misner-Thorne and Wheeler book, they wrote that interferometers have little experimental interest because of their low sensitivity. Then the people started working on gravitational waves, and the community realized at some point that the way to go was interferometers. And they started working massively on interferometers. And after 50 years and more than 20 attempts, there was the first direct detection in 2016. So we would like to start this journey now, a similar journey at least, hopefully with the same conclusion. And at the moment we are working on this. So the workshop that we organized was only a starting point. The collaboration now includes Valerie, who is at CERN, Fernando, and Jessica and Sebastian, who work in LIGO and are now in Maastricht. This is where they organized the old workshop. And we have recently welcomed Nancy Agarwal, who is at Northwestern, if I'm not wrong, Andreas Ringwald, who is at DESY, and Mike Ruiz, who is now retired. He is the former president of the Royal Astronomical Society. And the idea is to develop a technology roadmap involving all the interested groups to discuss the possible technological advances that can be done. Then at some point organize a new meeting for which we already have fundings, and at some point start applying for funding. So if you're interested in this topic, please get in touch with us, because there's a lot of work to do. Okay, and with this, I'm done.
Okay, well, thank you very much, Francesco. Very nice talk. And just 1 minute delay, not bad. Any questions? Irene has a question.
Yes. Can you hear me?
Yes.
Yes.
Hi. Thank you for the talk. It was very nice. Maybe you mentioned it, but I missed it. There is a paper by Brown and Allen saying that one cannot have tunneling from nothing because it's like you can understand the nothing as the deepest ADS vacuum that you could have. So in the same way that you cannot up tunnel from ADS, you cannot up tunnel from nothing. So how does this, how does it work with the other papers that you
Brown and Dahlen, so I'm not sure about this paper. For sure, you're referring to Minkowski to de Sitter, the problem Minkowski to de Sitter, or de Sitter to de Sitter?
I was thinking now from nothing to de Sitter, or from nothing to Minkowski, and then how, that could be related also to Minkowski to de Sitter. But
yes, can I say something? Maybe I'm the chairman. No, I think that's a good point. That we're actually studying this particular case with my student Veronica Pasquarella, and I think it's a good question. For, even because just the tunneling up from ADS to another ADS is supposed to be forbidden. And now the tunnel of nothing, which is the limit, looks worse. The case of tunneling up from ADS to another ADS, it is something that has been somehow studied in this relatively old paper by Myers, Schenker, et al., when they were using ADS CFT to get information about inflation. And actually, in that paper, they had argued that was not possible because it was against the loss of information problem. However, that was before the real Takayanagi story about the entropy of in general defined as an area of the boundary. And if you now consider this the new generalization of what is entanglement entropy is, then you can see that this configuration that they consider, which is on one side, the ADS with the CFT boundary, and the other side will be the Sitter case, in which there's no boundary because it's R equal to 0 is the stream of the Penrose diagram. So then you compute that there's the corresponding state is also a pure state. So you start from a pure state and go to another pure state, whereas they were thinking that you start from a pure state and go to a mixed state. And so in that sense, that takes out the restriction about going up from ADS from a smaller to higher cosmological constant. So and I have to say that we learned that from one of the authors of the paper, from Schenker. He was talking to him, so he's, oh yes, but that's an old paper, and then we have learned that better now. So
that's interesting. I didn't know we have to revisit this idea that we cannot uptunnel from ADS.
Not only from ADS, yes. So I think that's an interesting, and that is also mentioned in that paper that you mentioned that of Brown and Dallin. And again, as Francesco said, the reason is the same thing. Is the background that gives you the zero probability. So then the solution at the end will be the same as Francesco mentioned for Minkowski. It's just you don't take the full Minkowski, just a section of it, a part of it, and that's the one that will give you the bubble. So then you can go from lower to higher. Yeah, but I think it's a very interesting question. Something that is we are exploring now.
Okay, thanks.
There are more questions. Let me see. Okay, Gia. Gia, are you there?
Yeah, I'm here. Hi.
Yeah.
Hi. Thanks. Yeah, thanks for the talk. And I have I mean, what worries me a little bit, well, not really a little bit, pretty much in these considerations is that when you do corpuscular resolution of the sitter, you discover that there is a quantum breaking time, which is much shorter. It scales as power law, as opposed to exponentially long time scale. And so that time scale, therefore, just nullifies all the exponentially small effects. Because what that time scale means is that the sitter goes out of semi-classical regime way before we can talk about any saddle point tunneling or anything like that. And and that's a fact. So now the problem is that you are ignoring an exponentially large contribution, and you are focusing on exponentially small one, yeah, I mean,
so basically you're saying that the semi-classical approximation wouldn't be correct.
Yeah, we showed that. We explicitly derived so-called quantum breaking time of the sitter, which is not an instability time, although it's called quantum breaking. Sometimes people confuse.
I see.
There's not an instability time. That's a time scale over which the sitter, as a semi-classical solution, breaks down. It goes out of semi-classical regime. A mean field approximation is no longer valid. And I mean, that's a fact. And for example, that's one of the indications why, but okay, this question is not about, but that's to me one of the very strong indications that the sitter is inconsistent in quantum gravity and you must find graceful exit before that time elapses. But let's put that aside. I'm just saying, if we are interested in understanding what happens to the sitter, we cannot ignore exponentially large contributions and focus on exponentially small ones. To give you an analogy, let's think about a black hole, right? So imagine I take a black hole and I use semi-classical approximation or a classical metric, and I think of a black hole as a classical object. And now I will compute a probability for a black hole to, I don't know, to disappear or to collapse or to explode in 2 photons or something, I don't know. A probability which is exponentially small. Of course, I can use saddle point approximation, and I will conclude that that probability is exponentially small. So therefore, the time scale that I have to wait for it is exponentially long. However, that timescale is meaningless because black hole will decay on a timescale which is exponentially shorter, and it is absolutely unjustified to extrapolate black hole as a classical solution over the timescales that are longer than its half decay time. Exactly the same is true in the sitter. That's my point, and unfortunately, this is totally ignored usually when we compute.
I see, but then, for instance, the Hartloging wave function, you are saying that it's inconsistent unless it goes out of the sitter state.
Exactly.
Before.
Right. Exactly. So at the minimum, what this indicates is that beyond half decay time, that is pretty similar to how black hole half decay time. The way this comes out, this quantum breaking time. Beyond this quantum breaking time, we have to stop thinking about the sitter as a semi-classically valid object. And now what happens after that is a separate question, extremely interesting question. That's a separate point, but that simply gives us a cutoff of validity of any semi-classical approximation. And and this cannot be ignored simply from what I see. And this is what sort of confuses me.
Okay, no, thanks for the comment. I mean, this is something that needs to be checked. There are many checks that can be done from different directions.
Right. I mean, it's not that there is anything wrong with semi-classical saddle point computations. I'm just saying that the time scale is so long that at the end of the day, it becomes irrelevant. And so that's, thank you.
Thank you.
Now, Elias?
Hi, yes, I have a question. You mentioned at some point instantons which break the 0.1,3 symmetry, that is that they depend on two coordinates. Now, do you really have such solutions?
We have in a year you have this instant. So these are not really instantons. These are
what are they?
These are solutions that only preserve the SO3 symmetry.
Yes, but I mean, how do you? So these are Lorentzian solutions.
Yes, Lorentzian.
So these are the solutions
they are computed on a fixed
you evolve
time
after the instanton. Is that what you mean?
Yes, these are nucleated at some.
Okay, I see. Okay, all right, thank you.
Yeah, it's not clear. So the whole point for us about this open versus closed is that it's not completely clear once you couple matter how they would evolve in time.
But they are not evolved by the equations of your gravitational theory.
Yes. One needs to.
So you mean you cannot solve the equations really?
We are in the process of solving them.
Okay.
To understand whether you get an open or a closed universe.
Okay, thank you.
Now, Sudaswatwa Brahma.
Hi, thank you. I have a very quick question. Do you have any comments, since you mentioned mini superspace models and also Lorentzian actions? Do you have any comment on this work by Turok for using the Morse theory or Picard-Lefschetz theory?
Yes, there is so basically they claim that there is some a technique to compute these integrals, right? That
right, which tells you which is the saddle point of importance. Sorry.
So there is a paper by one of our collaborators, Shanta De Alvis, that basically tries to compute the fluctuations around these mini superspace solutions. And he argues that there is really no preferred contour that you can choose. It's again a matter of boundary conditions. So again, it will be, so choosing that contour would be again like choosing a particular integration constant here, basically between this A and B. If I understand it, it's like choosing a boundary condition, but I don't see any real physical reason to do that. I cannot comment.
Okay, thank you. Thank you.
No, thanks a lot.
Okay, well, thank you very much, Francesco. And